and having amplitude 1. We can see that at that frequency, the sine wave is in the passband of the low-pass filter, so the low-pass filter has no effect. So the output of the low-pass filter is applied to the input of the high-pass filter. This magnitude of 1, frequency of 1 Hz sine wave is applied to the high-pass filter, but it's now in the stop band of the high-pass filter where it's attenuated by a factor of 0.1. So at the output of the high-pass filter, we have a sine wave of amplitude 0.1 and frequency 1. If we apply to the cascade a sine wave of frequency 10 kHz and amplitude 1, we can see that at 10 kHz we are in the stop band of the low-pass filter. The low-pass filter attenuates the signal before it's applied to the high-pass filter by a factor of 0.1. This signal is applied to the high-pass filter where it's multiplied by this gain of 1 and passed to the output. And because of the gain of 1, the high-pass filter has no effect on the input signal. So at the output, we have a sine wave of 0.1. Now, if we apply a sine wave of 70 Hz, this 70 Hz sine wave is in the passband of the low-pass filter, so it's unaffected. The 70 Hz sine wave is in the passband of the high-pass filter, so it's unaffected. So the signal passes through the cascade unaffected, up to 1. Now we could do this for lots of frequencies and form the overall Bode magnitude transfer function by connecting the tips of all of these spikes. And we would get a plot that looks something like passing through this 1 level and then attenuating down to the 0.1 level here. This is the transfer function of a bandpass filter, where frequencies within this band are passed unattenuated, but frequencies outside the band, here and here, are attenuated. So here I've drawn the Bode magnitude plot for the cascaded filter we've been examining, and I want to look at the plot and identify some of the parameters that determine the characteristics of a bandpass filter. Now, just like for a low-pass filter and a high-pass filter, there are cutoff frequencies associated with the bandpass filter. But because the bandpass filter consists of a combination of a high-pass filter and a low-pass filter, there are actually 2 cutoff frequencies where the magnitude of the gain is down by a factor of 0.707, or 1 over root 2 from the midband gain. For this filter, we have a midband gain of 1. We multiply that by 1 over root 2 to get 0.707. I draw a horizontal line at that level and find the intersection of that line with the Bode magnitude plot. It intersects in 2 places. At a low frequency to give us the low frequency cutoff, FL, and at a higher frequency to give us the higher frequency cutoff, F sub U. Now the bandwidth of a bandpass filter is defined as the distance in frequency between the upper cutoff frequency and the lower cutoff frequency. So bandwidth is the distance between these 2 frequencies, or I can write it in equation form as the bandwidth is equal to Fu minus Fl. Now another frequency associated with the characteristics of a bandpass filter is the center frequency. And by symmetry, you can see that the center frequency for this particular bandpass filter is 100 Hz. And it can be written as F0 is equal to the geometric mean of the upper cutoff frequency and the lower cutoff
frequency. Te tiro la
frequency.
vibra. Espero mi oportunidad en mi chat éxitos.
Another parameter that is defined for bandpass filters is the quality factor, or Q, where Q can be defined in terms of the resonance frequency or center frequency and the bandwidth. Q is equal to the ratio of the center frequency to the bandwidth. Now for a fixed center frequency, you can see that by decreasing the bandwidth, we have a higher Q. So the higher the Q indicates a more selective filter, in that the filter, because it has a narrower bandwidth, allows fewer frequencies to pass through. And finally, the last parameter associated with the bandpass filter is the passband gain, KPB, where again for this filter it has a value of 1. Now let's look at the actual mathematical expression for the transfer function of this cascaded filter that we formed from a first-order low-pass and a first-order high-pass. We know the overall transfer function would be the product of the two individual transfer functions, and I've written them out here. Here is the transfer function of the first-order low-pass filter, and here is the transfer function of the first-order high-pass filter. Now I've written f0, the minus 3 dB frequency, for the low-pass filter as FLP, and I've written f0 for the high-pass filter as FHP, so we can distinguish between the two. Now each one of these filters has associated with it its own parameters, KDC and FLP for the low-pass filter, and KPB and FHP for the high-pass filter. Now we know that overall associated with this bandpass filter are three parameters, K, the resonance frequency or center frequency f0, and Q, the quality factor. And with some algebra and a little bit of manipulation, we can solve for those three parameters in terms of the individual filter parameters. And I have given you the results here. In an additional extra lesson in this module, I derived these with the algebraic expressions, or from the algebraic expressions. But you can see that K for the overall bandpass filter can be written this way. The center frequency for the bandpass filter is written this way, and Q looks like this in terms of the individual filter parameters. Now, there are a couple of things to consider about this filter or to pay attention to. We have, remember how we have formed this filter, we have a high-pass filter and a low-pass filter, and we've combined these to get an overall bandpass filter that looks like this. With characteristics, it has an f0, it has a K, and it has a quality factor. It has its minus 3 dB frequency called FL, and it has another minus 3 dB frequency, the upper minus 3 dB frequency, that we call F sub U. Now, it turns out that if, here is F. Welcome back to Electronics. This is Dr. Robinson. In this lesson, we're going to look at cascaded first-order filters.